Every single day, modern civilization consumes an unimaginable amount of electricity that is generated at remote power plants and have to travel thousands of kilometers to reach our homes. But transmitting this immense amount of power over such massive distances efficiently all the way to our homes is not that easy. That's exactly where power transformers come in. Power transformers make this difficult task easy for us. These incredible machines make long-distance power transmission possible, keeping our entire world seamlessly powered with electricity. In this video, we are going to pull back the layers and look at the fundamental electromagnetic principle behind a power transformer, explore the exact inner workings, and break down every single one of its critical internal components. Without further ado, let's dive right in. Our power generating plants are usually located far outside the cities, near fossil fuel sources like coal mines, gas fields, river dams, or renewable energy sites. The electricity produced at these sites often has to travel hundreds of kilometers through transmission lines to reach the consumers. When transmitting electricity over long distances, there are only two practical choices. We can either transmit it at low voltage and high current, or a high voltage and low current. That's because the amount of power we need to deliver remains the same, and power is the product of voltage and current. But here's the catch. As electricity travels through the transmission lines, some of it is inevitably lost as heat. That loss is given by the equation. Power loss is equal to the current squared multiplied by the resistance. Notice that the current is squared. That single detail makes a huge difference. Because current is squared, even a small increase in current causes the power loss to rise dramatically. So, if we want to minimize transmission losses, reducing the current is the key. And the only way to reduce current while delivering the same amount of power is to increase the voltage. That's exactly why when electricity is generated at a power plant, it is first sent through a step-up transformer that raises the voltage to hundreds of thousands of volts. Transmitting electricity at such high voltage allows it to travel over long distances efficiently by reducing the current and minimizing energy losses along the lines. As the electricity approaches the city, it passes through a substation, where a step-down transformer lowers the voltage to a safer level for subtransmission. The power is then carried through subtransmission lines to a distribution substation, where another step-down transformer reduces the voltage even further for local distribution. Finally, pole-mounted or ground-mounted transformers in the neighborhood step the voltage down one last time to the safe and usable level required for homes and businesses. Now that we understand why transformers are essential, let's look at how they actually work, starting with the fundamental law of electromagnetic induction. Whenever current flows through a wire, it generates a magnetic field around it. If we reverse the direction of the current, the polarity of the field also reverses. To amplify this effect, we wind the wire into a coil. This concentrates the magnetic field, making it much stronger and focused. If we supply the coil with direct current, the magnetic field remains static and stationary, because direct current doesn't change magnitude or direction on its own, making it incapable of performing work on a nearby conductor. If we place a second coil next to it and connect it to a load, no energy is transferred because the magnetic environment remains unchanged. However, if we replace the direct current with alternating current, the voltage and resulting field fluctuate continuously in both magnitude and polarity. This causes the magnetic field to continuously expand and collapse. As this fluctuating field from the first coil expands and collapses, it cuts through the second coil, inducing an electromotive force or voltage in it, and that creates a flow of electrons known as current. This process, called mutual induction, allows for the transfer and transformation of electrical energy without any physical connection between the two circuits. To ensure the magnetic energy isn't wasted, we place a loop of ferromagnetic material, like laminated iron, between the coils. This core acts as a low reluctance path, perfectly linking the magnetic flux from the primary to the secondary winding. To maximize efficiency, the iron core isn't a solid block. Instead, it's constructed from thin sheets of iron, stacked together and meticulously insulated from one another. This clever design is engineered to disrupt internal loops of electricity that try to circulate within the core, known as eddy currents. By breaking these currents up, we prevent the core from overheating and wasting energy as heat, ensuring a near-perfect transfer of power. The coil connected to the source is known as the primary winding, while the coil connected to the load is known as the secondary winding. The EMF induced in the secondary winding is related to the number of turns in the coil. So we can actually control the output by varying the number of turns in the secondary winding. To step up the output voltage, we use more turns on the secondary winding. To step down, we use fewer turns on the secondary winding. So far, we've looked at basic single-phase induction. But for massive power transmission, we don't use single-phase, we use three-phase power. A three-phase AC supply consists of three individual alternating currents, perfectly spaced at 120 degrees apart. This overlapping power delivery is far more efficient for transmitting massive amounts of power more smoothly and efficiently than single-phase, making it ideal for transmitting large amounts of electricity over long distances. To handle this, we use three-phase transformers. Now let's build one from the ground up, starting with the core. The core is built from thousands of thin sheets of cold-rolled grain-oriented steel laminations, carefully stacked to form three vertical columns known as limbs. These limbs are connected at the top and bottom by horizontal sections called yokes, creating a complete magnetic circuit. If the core were made from a solid block of metal, the constantly fluctuating magnetic field would induce massive eddy currents, resulting in significant energy loss and overheating. To prevent this, each lamination is coated with a thin layer of silicate-based ceramic, known as C5 insulation. This coating is extremely thin to allow maximum steel in the core, yet strong enough to withstand high operating temperatures and break the path of eddy currents. To ensure a smooth magnetic flux, the corners of the core are mitered at 45-degree angles. This allows the magnetic flux to easily turn the corner, minimizing vibration and heat. The core laminations are secured using high-strength austenitic stainless steel straps. Because austenitic stainless steel is essentially non-magnetic, it minimizes interference with the transformer's magnetic circuit while providing the high clamping force required to keep the laminations tightly compressed. The sharp edges of the core are carefully wrapped with multiple layers of high-density craft paper. This provides robust insulation and mechanical protection for the coils that will sit around it. The low-voltage winding is always placed closest to the core. This is because it operates at a much lower voltage rating and requires less insulation between itself and the core. This placement saves both space and material. The windings are made using copper conductors that are first coated with a thin layer of electrical enamel. This enamel provides insulation between individual turns. For additional mechanical strength, the coils are carefully wrapped with multiple layers of high-density craft paper. This combination of enamel and craft paper creates a highly reliable insulation system capable of withstanding high voltages and high operating temperatures for decades. The winding conductor itself is not round, but rectangular in cross-section. This rectangular shape maximizes the space factor, meaning we can pack more conductor material into the available space compared to circular conductors, which leave unused gaps. To handle the very high current on the low voltage side, engineers often use a helical winding configuration. This design consists of a continuous spiral copper strip wrapped around the core, resembling a large spring. This design accommodates large conductors and is highly effective because its geometry allows efficient oil circulation for cooling, while also providing the mechanical strength and resilience needed to withstand high current stresses. To ensure these coils remain stationary under the immense mechanical stress of high voltage surges, engineers use high-strength pressboard axial spacers and radial spacers to hold the windings firmly in place while also serving as cooling channels, allowing dielectric oil to flow freely and carry heat away from the assembly. Once the low voltage winding is firmly secured, a thick layer of insulation is applied over it before the high voltage winding is placed on the outside. The high voltage winding uses thinner conductor since it carries lower current, but it must withstand extremely high voltage. To manage this high voltage, engineers employ a disc winding technique, which provides excellent insulation control and distributes voltage stresses evenly across the winding. In a disc winding configuration, the conductor is wound in a series of flat discs that follow a continuous alternating spiral. One disc is wound from the inside diameter toward the outside, creating an outer crossover, while the adjacent disc is wound from the outside back toward the center, creating an inner crossover. This zigzag pattern creates excellent voltage distribution across the entire winding and gives the coil outstanding mechanical strength to withstand the huge forces that occur during short circuits. Many large power transformers used in transmission networks employ a combination of star and delta connections across their high voltage and low voltage windings. In one common configuration, the high voltage winding is often connected in star, reducing the voltage stress on each winding and providing a neutral point that can be grounded for improved system protection and fault detection. Meanwhile, the low voltage winding is connected in delta, providing a closed path for circulating third harmonic currents. This helps suppress voltage distortion, improves power quality, and enhances the overall stability of the electrical system. Because the grid voltage constantly fluctuates with changing consumer demand, maintaining a stable output voltage is critical. Transformers achieve this using taps. These are specially placed connection points along the winding that allow the transformer's turns ratio to be adjusted. Taps are almost exclusively placed on the high voltage windings. By positioning the taps on the high voltage windings, we leverage their outer position for easier accessibility and their higher number of turns for pinpoint precision. Since the current level on the high voltage side is also lower, it minimizes the risk of electrical arcing on the contacts during a switch. The device responsible for the turns ratio adjustment is the on-load tap changer, or OLTC. The on-load tap changer is a highly sophisticated electromechanical system that allows a transformer to adjust its turns ratio without interrupting the power supply, ensuring continuous and stable voltage regulation across the grid. To properly understand how it works, let's have a look at this simple mechanism. Under perfect conditions, when the grid is perfectly steady, the system sits on the 100% nominal tap. But the grid's voltage is never perfect. It always fluctuates. For instance, when a big factory suddenly switches on its heavy machinery, the voltage across the entire network drops. The on-load tap changer detects this and quickly shifts to a higher tap position. This includes more turns to the secondary winding, boosting the output voltage and bringing it back to normal. Conversely, if the voltage surges due to a sudden reduction in load, the mechanism quickly shifts to a lower tap position, reducing the number of active turns and bringing the voltage back to normal. An on-load tap changer mechanism consists of two primary functional units: the tap selector and the diverter switch. When the automatic voltage regulator of the transformer detects that the output voltage is too high or too low, it sends a command to the system's motor drive. The motor rotates the drive shaft connected to the tap selector, which first moves the tap selector to the new desired tap position. Once the selector reaches the correct tap position, the diverter switch quickly transfers the load current from the old tap to the new one. This process follows the make-before-break principle, ensuring the circuit is never opened and the load current flows continuously without interruption. The taps are divided into two groups: odd-numbered taps and even-numbered taps. Each group is handled by its own tap selector. In this illustration, the diverter switch is currently connected to the even side at position 6. To switch to tap 5, the selector on the odd side first quietly moves to position 5. Since it is not carrying any current yet, the movement creates no arcing. Once the next tap is pre-selected, the diverter switch performs a fast changeover to the odd side. This transition happens in just a few milliseconds and uses transition resistors to temporarily limit the current, ensuring the load is never interrupted. Let's slow things down a bit and watch that switch again in super slow motion. During this critical moment, the diverter switch follows a precise sequence. First, it opens the connection to the old tap position 6. As it does so, it instantly inserts one transition resistor into the circuit. The full load current now flows safely through this resistor. Next, the diverter moves into a very brief intermediate bridging position. Here, it simultaneously connects to both the old tap 6 and the new tap 5. At this exact moment, both transition resistors become active in the circuit simultaneously. These resistors limit the circulating current between the two taps and prevent dangerous arcing. As the diverter approaches the new tap position, the first transition resistor is bypassed. Once the new tap connection is fully established, the second transition resistor is also removed from the circuit, allowing the load current to flow directly through the new tap. This entire switching process happens very fast with no interruption to the power supply. In real-world operation, an on-load tap changer in a busy distribution transformer can perform anywhere from 10 to 50 tap changes per day, depending on how much the load fluctuates. Once every connection is secure, all the internal components are enclosed in the main tank. The terminals of the low voltage and high voltage windings are brought out of the transformer tank through bushings. The bushings are designed to withstand high electrical and mechanical stresses. Even though power transformers are incredibly efficient, often reaching 98% to 99% efficiency, a small percentage of energy loss still exists in form of copper losses, eddy current losses, and hysteresis, which generates significant heat. If left unchecked, the heat would raise the temperature of the winding and core, reducing the transformer's lifespan and efficiency. To manage this heat and maintain safe operating temperatures, the transformer's main tank is completely filled with a special insulating mineral oil commonly called transformer oil. This oil is a dielectric fluid that serves as a powerful electrical insulator and cooling medium, carrying heat away from the copper coils to the external radiators attached to the transformer tank. These radiators contain multiple hollow tubes that allow the transformer oil to circulate through them. They greatly increase the surface area for heat dissipation. The cooling process operates on the principle of natural convection. First, hot oil inside the main tank becomes less dense and rises to the top. Then, it flows into the radiator tubes through the top header pipe. As the oil flows downward through the hollow radiator fins, it transfers its heat to the surrounding air through the metal surfaces. The cooled oil becomes denser and sinks, returning to the bottom of the tank through the bottom header pipe. This creates a continuous thermosiphon effect, a natural rising and sinking cycle that circulates the oil throughout the tank without any pumps. Air passes naturally through the spaces between the radiator fins, carrying the heat away. This method, where both oil and air move by natural convection, is called oil natural, air natural. For larger transformers that produce more heat, fans are mounted near the radiators to blow air forcefully across the fins. This cooling method is known as oil natural, air forced. An additional tank known as a conservator tank is used to store excess transformer oil. The conservator is connected to the transformer's main tank, and it ensures that the tank is always completely filled with oil, while also providing a space for the oil to expand into as it heats up. As the transformer oil heats and expands, it forces air out of the conservator tank. When the oil cools and contracts, the tank pulls air back in. To prevent this air from introducing moisture and dust into the oil, which will degrade the oil's insulating properties, the air is pulled through a silica gel breather. This device contains desiccant crystals that absorb moisture and other impurities from the incoming air, ensuring that only dry, clean air enters the system. The blue color of the silica gel indicates it is dry and active. When it becomes saturated with moisture, it turns pink, signaling that it needs to be replaced. Mounted on the pipe connecting the conservator tank to the main transformer tank is a protective device called the Buchholz Relay. This device monitors the transformer's internal condition by detecting the gradual accumulation of gas caused by overheating or insulation failures. It also detects sudden surges of oil caused by severe internal faults, such as short circuits. By sensing these changes instantly, it can trigger an alarm or trip the entire system offline, preventing a minor fault from turning into a catastrophic failure. Thanks to systems like these, the electricity that powers our homes, hospitals, and industries flows safely and efficiently every single day. If you enjoyed this video, feel free to leave a like and continue exploring with the next video on your screen.